intermolecular forces. There's 3 types. What are those 3 types? According to your notes. Okay, we got dipole-dipole forces. Okay, well, what has to be present for us to have a dipole-dipole force? What do we have to have? Polar bond, right? Thomas, you gotta have a polar bond. So you gotta have the difference in electronegativity that ranges between 0.3 and 1.7. You have to have that. Okay? If you don't have that, you can't have a polar molecule. So a lot of times I'll reference polar molecule. Hey, right here I've got a polar molecule. All right? Polar molecule just means that it has a polar bond where the electrons are shared not equally. So if I've got a polar bond, what I'm going to do, how to show it, I'm going to show the arrow pointing toward above, pointing toward the atom that has a greater electronegativity. Chlorine's 3, hydrogen's around 2, so we know the difference is 1, and we know this is a polar molecule. So then if we have several polar molecules floating around, then we know that opposites attract to those molecules, and it creates, this is a dipole, and this is a dipole. So how do they interact? Dipole-dipole interaction, meaning opposite sides will attract one another because they have opposite charges. Any questions on that? So that's all you would have. If I would have Cl bonded to Cl, this is nonpolar. So we cannot have polar or dipole-dipole interactions when we have something nonpolar. So this cannot have dipole-dipole. This is dipole-dipole. Any questions with that? You have some other drawings in that with that. Any questions or thoughts? All right. So could you draw that if you needed to? If I give you one, you draw the molecule out. You know how to draw the Lewis structures out. And then you can go ahead and show the arrows pointing from the one with the lower electronegativity to the one with the higher for all the bonds. Okay, good. We'll probably have you do that later on, maybe Thursday or Friday, to kind of finish up ideas. So what's the second one? And this one is probably the biggest of the free forces. If molecules have this, then they probably hold together really, really well. Now you're going to hear me talk about boiling point and melting point. You guys remember the lab we did with ionic, molecular, and metallic? Do you remember the covalent ones, what their melting points were? They were lower. Why are they lower? Is because what holds them together is just intermolecular forces, which are not very strong. They're not as strong as ionic would be. But what we'll do is we'll use boiling point to tell us if there's strong intermolecular forces of attraction. Okay? If it has a high boiling point, that means before they go from the liquid phase to the gas phase, they're going to have to be separated out. And so if there's stronger forces that hold them together, they're going to be harder to separate out. If there's not very many forces that really hold them together, they're going to be easy to separate into the gas phase. Okay? So we're going to do a lab tomorrow based upon evaporation. Evaporation is another one you can look at. If something evaporates really fast, then the molecules don't want to stay in the liquid form. They won't want to attract one another as great as something that evaporates slow. Something that evaporates slow, turns into vapor not very easily, is going to have stronger intermolecular forces if they're molecular. Okay? So the next one was hydrogen bonding, right? So what hydrogen has to be bonded to what 3 elements to exhibit hydrogen bonding between the molecules?
Nitrogen, oxygen, and fluorine.
Yeah, nitrogen, oxygen, fluorine. So the one example I gave you yesterday was water. This is just review. Now, we focus upon the definition, and the definition says it's an attraction between a hydrogen and an unshared pair of electrons on another molecule. So we know this is polar. I'm drawing my arrows better today. Got a little practice. Okay? So what happens, this hydrogen is highly positive because it's bonded to an oxygen that really takes a big chunk of the electrons that are shared. And because of that, it's positive, and it's going to be attracted to negative electrons, which is the unshared pair. So here's the unshared pair. Okay, any questions on that? Makes sense? So this is not dipole-dipole we're showing. Now, we could show dipole-dipole with this as well, but we're not going to show the unshared pairs of electrons because we don't want to confuse. We don't want to confuse it. Okay? Because it's more attracted. This region here is positive. This region is negative. Negative. So it's the region that's attracting it, not just one particular hydrogen. So maybe be showing that the hydrogen is probably not right. Maybe be showing attraction between the region to that region is probably a better way to show it. Okay. Questions on the first two? The third one, I need you to go ahead and write notes on. That is the new. It's called London Dispersion Forces. And then we'll talk about specifics of London Dispersion Force. Okay, go ahead and write that out. Now we're going to take an atom that doesn't have very many electrons and show it to you. And so, the top of page 207, we'll make a drawing of that. Okay. So here would be our nucleus. And here would be our electrons on this side. Okay. Here's another atom. We'll say it's over here. And it has its electrons, and they're distributed pretty equally. Let's say this atom has 2 electrons. This would be like helium, for example. And we take a snapshot, and then this atom has electrons that are distributed evenly, one on each side. And this one, they're distributed unequally. They're both on one side versus the other. Okay? So what that does is it induces this one. So if the electrons are on this side, this left side here is negative. The one on the right, it will cause those electrons to line up to be on the same side, because this side's over here. This area here is going to be positive, and this area right here is negative of this atom. So it's going to cause this one to induce and look like this when it comes in close proximity to it. So when that atom gets close to this atom that has a side that's slightly positive and one that's slightly negative, it induces the electrons to line up. That's just one example. So it induces. I'm going to induce this process to happen. So there's an attraction between these two sides. And that's what we call London dispersion forces. It's not as easy to draw, but that's what happens. Okay, that's what's going to happen. Okay, so let me give you some examples of what you'd look for a molecule or an atom to have larger London dispersion forces. So these are scenarios. Well, if it has this, it has larger dispersion forces. If it has this, it has smaller dispersion forces in comparison. Okay. Sometimes you compare apples to apples and oranges when you do London dispersion forces. You have to do that so that you can compare and see what's happening. Okay. So when we take a look at examples, these have larger London dispersion forces. large atoms or molecules. They have larger London dispersion force. So if you have a larger atoms or molecules, you have larger dispersion forces. Why? More electrons. If you got more electrons that are lining up on one side versus the other, then you have greater attraction that'll take place between those molecules. So if we've got larger atoms and larger molecules, we have larger number of electrons. Okay, does that make sense? Anytime where we can create more electrons moving and dispersing unequally, then we have greater attraction between those atoms or molecules. Got it? Another way we can look at this, larger dispersion forces would be when we have a large molar mass. And when I say large molar mass, sometimes we don't have the molecules drawn out for us. So if we don't have the molecules drawn out for us, then we don't know, if they do have, if they're larger. Okay? So what we're going to do is we're going to look at large molar mass. In the lab is called molar weight. Okay? So if you see something that has a large molar mass compared to something that has, we're going to look at that here in a second, versus something that has a smaller molar mass, it probably is going to have greater London dispersion forces. Okay? And the last one kind of goes along with the first one, but it has to do with the length of the molecule. So we can have larger atoms and larger molecules by weight, like the molar mass, but we can also have longer molecules. So longer molecules. That's going to be really important. These three topics are going to be really important in the lab we're going to do tomorrow. Very important to know that if it has larger, so we could say smaller London dispersion forces, we could say smaller atoms, molecules, smaller molar mass, smaller molecules. We can say all those things. And that would be okay, because we're just looking at it in a way of looking at smaller London dispersion forces. Got one scenario I want to share with you, and then I'm going to show you how to do your first part of your lab. So the scenario we're going to look at involves these are all your halogens. Okay? So we're going to look at molar mass, and we're going to look at boiling point. Okay? So if I want to find a molar mass, I have to take and look at how many atoms I have, and then I multiply it by its weight. So fluorine, you have 2 fluorine atoms, and so I'm going to look at its weight on the periodic table per mole that it has. And fluorine has a mass of 19, right? 19. So I'm going to take it times 2, and so its molar mass is 38 grams per mole. Okay. I'm going to look at chlorine. Look at its weight. It's 35.5. I'm going to go ahead and multiply it times 2. So that's going to be 71. Okay? Then I'm just going to continue to do that for bromine and iodine. Do the same thing, multiply just by 2 each one of those. And when I do, and I'm rounding these, okay? I'm going to come up with 160. And then iodine, I'm going to come up with 254. Does everybody know how to come up with those numbers then, right? Just multiply. All right. So now let's look at the boiling points. We're going to go ahead and write down the boiling points. If you guys would turn to page we can get most of these boiling points down off of page 204. Okay? 204. So turn to page 204. And I'll write down the boiling points here real quick for you. So I have to transition from Celsius to Kelvin. So. These are just estimates, but we look at the boiling points for these four. I think this is like around negative 192. This is a negative 183. Bromine is a minus 34. Or is it 34? Oh. Bromine's 59, I'm sorry. So this would be minus 34. Then bromine is 59.
And this is in Celsius?
Yeah, and these are Celsius. And this is 180. And these are all in degrees Celsius. Okay. Just to finish up our thoughts. When you look at fluorine, it has the lowest molar mass. So there's a trend in molar mass, right? It gets bigger. And the boiling point, what happens to it? Gets bigger, or larger boiling points. Okay? All right? So, does any of these have dipole-dipole interactions? Does fluorine through iodine, does any of those have dipole-dipole interactions? They're the same. Okay? So they would be the same. Does any of them have hydrogen bonding? No. The only thing they have going for them to hold them together is London dispersion forces. Remember we talked about the larger the molar mass, larger dispersion forces, right? So look at them. They're all have larger dispersion forces, and that correlates to boiling point. The bigger the boiling point, the larger dispersion forces that they'll have. Okay? All right, real quick, I'm running out of juice here. We want to do number one all the way across. I'm going to help you with number one. So on your lab sheet, number one is ethanol. C2H5OH. C2H5OH. So if you got your lab sheet in front of you, then we're going to go ahead and fill out the first portion, and then you can fill out the rest on your own in class with the time remaining. Carbon's going to be the middle because it needs the most electrons. So we haven't done anywhere we have long chains, but we always know carbon goes in the middle. So there's my carbon. Goes in the middle. Then hydrogens are always around the outside. So C2, we have 5 hydrogens off of those carbons. So here's my 5 hydrogens. C2H5. Now the OH tells you it's off the end because the H is not with those 5. O and H are bonded together. So we'll put a bond O. We'll show our 2 unshared pairs of electrons off of that O. And then we'll show bonded to H. So that's ethanol. Okay. So what basically you're going to do is you're going to have a carbon chain of 2, 3, 4, 5, 6 carbons long. They'll be all in a row. And then the hydrogens all surround them. If you have an OH, it goes off the end. And it goes off the end like that. So the next thing we're going to do is find the molar mass. Well, it's just like I did with fluorine, chlorine, bromine, and iodine. I'm going to count how many carbons I have. Carbons, I have 2. Hydrogens, I have 6. Oxygens, I have 1. Each one of those would represent moles I have. So I got 2 moles of carbon, 6 moles of hydrogen, and 1 mole of oxygen. If I want to find the weight contributed by each atom, a mole of it, I take it times its atomic weight. So carbon's atomic weight is 12. I'm rounding. So that'd be 24. Hydrogen, it takes 1 gram to make a mole of that, and I have 6 of them, so I'm going to take it times 1. And that gives me 6. And then oxygen, I'm going to take times 16, and that gives me 16 at the end. Then I add them all up, and that'll be my molar weight. So 24 and 6 is 30, plus 16 is 46 grams per mole. Questions? Pretty easy? Okay, so that's what you're going to do on test tubes 2 through 6. Okay, good. Last question. Hydrogen bonding, when we look at our structure, we look for hydrogen bonded to an oxygen, nitrogen, or fluorine. And since we don't have nitrogen or fluorine, we look for a hydrogen bonded to an oxygen. So does this exhibit hydrogen bonding? Yes. It does because of the OH.
So if there's an OH, it'll be a hydrogen bond, and if there's not,
yeah,
it won't be.
Pretty much. But you want to look at your structure just to make sure. Okay? And so you need to do for tomorrow those first 6, draw them out. That kind of gives us an idea of the length of the chain. So you kind of know what we're getting to here. Length of the chain. Greater dispersion forces we're looking at. Okay? We can check it tomorrow. I can look at it real quick.